What up, nerds? It's Jason here from Custom Cans, and this week we're going to be talking cables, and you can win this fancy cable with fancy aeco connectors. Tell you how in a bit. But yeah, a little while ago, aeco sent us a load of connectors to try out. I'm designing some new cables for us and another company in Cheltenham. So yeah, trying out some different connectors. But yeah, these aeco ones, certainly their 4.4s were really good. So we're trying out some of the other ones. Thought it might be interesting to see how we would make a braided cable like this. Yeah, it might also be fun just to do a few calculations for skin effect and capacitance and that kind of stuff, and just see what we're looking at, what differences they make. That kind of stuff. But it's just there's so much to cable design. Like ergonomics, how it feels and stuff is probably as important as anything else. So yeah, so trying out this is quite a nice soft cotton cover on this one. So if you want to learn a bit more about cables, see how they're made and that kind of stuff, join me in the workshop. Now then, I must apologise because the sound and video probably isn't ideal. I've been banished to the corner of the workshop before I had a desk, you know, with the other technicians. But apparently what I would call prototyping, they call a shit ton of mess. So I've been banished to the corner, and the acoustics and stuff aren't as good. So we'll sort it out. But anyway, over to workshop, Jason. Good morning, my nerd friends. It is Jason here from Custom Cans, and today we're probably going to be making a cable and going through some cabley stuff, doing some sums, poking some science, that kind of thing. Yeah, basically I'm looking for something to give away because we've done our 10,000 subscribers, and then I remembered that aeco were kind enough to send us some very fancy looking connectors to make cables out of, possibly do a video with. So we'll do that, we'll make a cable, we'll go through some of the things, and then one of you can have it. We're going to make it with 3.5mm jacks, so it'll fit any hi-fi man, Denon, anything that takes 3.5mm jacks. We'll make it kind of universal. For this recipe you're going to need some relatively fat Litz wire, some cotton piping, appropriate flux and solder, and la-di-da fancy big boy connectors. And also handy, soldering iron, soldering cleaner, some kind of mat that you can possibly get solder and shmoo on. All these things are vitally important. Okay, well, let's begin. So the plan is, I think if I make the cable 2 meters, that's probably a nice length. You know, it's not too long, it's not too short. And the first problem that we're going to be having is getting this wire down this here sleeve. Now then, obviously you can poke it in. So I've chosen this because it's basically a cotton tube, and we're going for natural fibres here. It's natural silk covered Litz. So you could just poke that in, maybe tie a knot in the end and just wiggly worm that down. I'm going to use a wire, so I'm going to stick a bit of wire down here, tie it to the end of this. So I've got a bit of like piano wire that I'm going to stick down the end of this, tie it to the end of this, pull it through, Bob's your what's it. Right, the first little bit of nerdy stuff we'll go over is this wire. So this is Litz wire, which means every one of those tiny little strands is individually insulated, so they don't conduct electricity from one to the other. That means that you've got hundreds of tiny little, just over 100 tiny little wires rather than one big fat wire. And you're thinking, what difference does that make other than it being more flexible? Well, this is where skin effect comes in. It probably has very little effect over audio frequencies, but it can't hurt. This is quite fat, as you can see. It's probably over 1 millimeter across. And let's hand over to science, Jason, to figure out whether skin effect would be a thing if this wasn't Litz wire. So if we look at this first slide, you'll see inside a round conductor an AC signal, so alternating current going backwards and forwards, creates little magnetic eddies inside the wire, which essentially push the current to the outside. So DC, if it was just direct current, there'd be none of this. You'd just be using the whole thickness of the conductor. As the frequency increases, that current gets pushed towards the outside, which means that there's less of the actual wire being used, so the impedance goes up. So at very high frequencies, they have a higher impedance than low frequencies, which are going through the whole cable. So here's another diagram that basically shows that. So you can see on the outside you've got the maximum kind of current flow, and in the center the current is not flowing as much. And that bit there is the skin depth, which we can calculate. So you can put in a frequency and you can see at what point this is going to be a problem. On the other side you can see the formula for calculating this, and at the bottom the W is the frequency. So as you can imagine, as it's the number being divided by the frequency, the higher the frequency, the smaller that number gets, so the smaller the skin depth is. So let us plug in some numbers and see. So what I'm going to do here is put in 20 kilohertz, which is kind of the top of human hearing range, outside a lot of older people like me's hearing range, but it's the kind of the upper limit of most people's hearing is around 20 kilohertz. If we plug that into the what's-it, we get, for a copper conductor, a round copper conductor, we get a skin depth of 0.461 millimeters. So what that would mean is if the radius, so half the diameter, the radius of the wire is greater than that number, greater than that amount, so greater than half a mil, skin effect is going to start to come in at 20 kilohertz. So it means that if you've got a fat wire, so the wire that we're using, where is it? This one, it's around 1.2, 1.3 millimeters in diameter. So if that was standard wire, you would definitely start to get some roll off in the high frequencies. It's minimal, you know, but it's measurable. You would get a tiny bit of loss at the top end if it was standard wire. Because it's lit wire, it is many, many small wires individually insulated from each other. And those wires are, what is it, 0.08 millimeters. So crazy high frequencies you'd have to go up to before skin effect came into a thing. But yeah, so that's something to take into account. So if you're using very fat wires to make a cable, at the high frequencies you're going to get a slight roll off unless you use lit wire. But as I said, these effects are minimal, probably not audible or measurable, but you know, if you can make it better, why not? The reason for choosing a fattish wire is basically lower impedance. So if you double the cross-sectional area of copper, you halve the impedance. So the fatter wire you get, the less resistance, the less of your music is turning into heat, and the more of it is going into your headphones. And again, it's negligible, but can't hurt. Might as well go fat if you can. So what I'm going to do is measure out 2.2 meters. I know you're thinking you're making a 2-meter cable. Why are you measuring out 2.2 meters? Well, my dear friend, we're going to be making a braided cable, so it's not going to be straight. So let's have my 0.2 on. There we go. Yeah, and during the braiding process, you're going to lose a bit of length, and I reckon that's about 10%. It's not going to be super accurate. I've not made it with this piping before, but I reckon 10% is a fair whack. We're going to end up somewhere around 2 meters. Just cut there. Yeah, once you've got your first one, you can then measure the others up against it. Trim those off so they're all the same. Cool. I've made a length of wire basically just over twice as long as the thing. So this is like close to 5 meters of wire, because I'm gonna fold it in half so we got twice the thickness and twist it, because why not? Yeah, twisted pairs, always fun. The main aim is that we're just getting twice as much goodness, twice as much copper, half as much impedance, and it was already quite a fat thing, so this is gonna be super dope. Right, now we have our wire through our cover. Let's have a look at the main jobby that we're going to be playing with here. So we're going to go with a aeco 4-pin XLR. It's a very nice looking bit of kit. Let's have a look. So there we go. So there's the pins that we're going to have to solder through, gold plated, and in there that's the neck that our wire is going to go through, and you can see that it's got a reducer there, so if you've got a fatter wire you can take this centre part out. Yeah, it's just a little grub screw on the side here, you can take this out, so you've got a really fat cable. I don't know, ours is going to be pretty fat, but I think it's going to squish down a bit as well, so we'll probably leave that centre bit in here. Okay, so next bit of preparation. I've got some flux here. I'm just going to add a bit of flux to each of these pins that we're going to be soldering to. And that'll just help Get a good solder joint on there. It helps conduct the heat and also cleans the surface. I think it's going to be easier to solder on the other end first, so we'll get this jack out. Oh, look at that! That's a beautiful steel body on that bad boy. Just undo that. Yeah, that is nicely machined. Nice, nice. Cool, right, we have our jobby here, and you've got tip is normally positive, ring is normally negative, so we're going to connect up these two, and then that should make it compatible with Hi-Fi Man or Focal or Denon. They all use a similar kind of setup. So we're going to have one wire on the negative, one wire on the positive, and just leave the other one disconnected. So a little bit of flux on the various bits I want to solder. Start with the negative terminal. Just heating up the thing I'm soldering to, and the solder flow nicely. Yeah, I was probably a little bit over ambitious with the thickness of this wire. What I'm going to do is I'm just going to wrap that in PTFE tape, insulate it from the other one, and help us not get a bridge when we try and do this. I'm regretting this already. I'm going to say definitely don't use a wire this fat. Like one lot of the 112 by 80 would have been alright, but 2 lots is too many lots. Okay, now we have both your ends on, we're going to want to twist and then braid. And for this, it's easier to twist them in opposite directions initially, until you've got the kind of length you want for the Y-split. Okay, we get up to the right kind of length, we're going to braid. Join the two together. I'm going to do a flat braid. Now then, why are we braiding and twisting, you may ask? Well, obviously it joins the two cables together. But it also has some other advantages. Okay, braiding has some advantages, but essentially one of the main things it does is it will drop the capacitance of the cable. If we look at the symbol for a capacitor, it's 2 plates in parallel like that, and that is essentially what most headphone cables are. They're a conductor, a wire thing, and an insulator, and then another wire, and that builds up a charge. The capacitance is very low on most cables, and again this effect is probably negligible, but again it can be reduced by separating the conductors. So if you get those plates, you separate them, it's going to reduce the effectiveness of the capacitance. If you get a dielectric closer to that of air or something like that, again that's going to reduce your capacitance, the separating material that's in there. So because ours are silk wrapped and we're using cotton on this cable as well, it's mostly air that's separating those conductors. That's going to reduce that capacitance. So what's the dealio? What's the problem with having capacitance in a cable? And as I've said, very small effects. There's kind of 2 things to think about when we're looking at the capacitance of a cable. Capacitive reactance. A capacitor, as we saw, it's 2 plates, they're not connected, so if it was a DC current, no current would flow. Because we've got an AC current, it's building up a charge, and then when it flips the other way, it releases that charge and builds up an opposite charge. So past a certain frequency, it's going to start transmitting power across those plates. So essentially, again, when you get up to very high frequencies, it's going to be like you've got a resistor across the 2 wires bleeding some of those high frequencies back to your player. So very high capacitance, you would lose top end again. It's going to bleed off those very high frequencies back to the player before they ever get to the headphones. So a very long cable, badly designed, straight wires, going to have high capacitance. It's going to bleed off some of those high frequencies. But how bad is it? Let us have a quick look. So I've got my little LC meter here, which will measure the capacitance of a cable. And the capacitance of cables is very small, normally. I've seen, like, the HD 600 is one that springs to mind as one that was quite high. It was like 600 picofarads for a 3 meter one. So what I've got here is a 1.5 meter cable from a pair of Grado SR80s. If I just zero our LC meter, snap that on there, and we are measuring 244 picofarads, 244 picofarads for this cable with no connectors on the end. The connectors normally add 5 to 10 picofarads. So with no with nothing on the end, it would be slightly higher than that with something on the end. But 244 picofarads. I've done a quick calculation down here somewhere at 20 kilohertz, which again is our upper frequency that we're looking at. 240 picofarads is going to be 33 kilo ohms, so 33,000 ohms of resistance placed across that. So it's very high resistance. So the headphones are going to be much lower resistance. It's going to be a lower resistance path. So it's going to make, very little difference. But lower is better. If you can lower that capacitance, you can stop that from happening pretty much. So, I don't know, let's have a... I've got one of our ultimate cables here. Let's just measure this. Just showing off now. 0. So, ultimate cable, we're getting... This is a 1.5 meter again. 18 picofarads, much less. Oh yeah, more than 10 times less than the other one. So yeah, so that's pretty good, and then I don't know, we've got one of our ultra low capacitance cables, which are designed to have low capacitance, but aren't quite as crazy as the ultimate cables. Let's see if I can get this on 0. And there we're getting 21, 22 picofarads. So again, very low capacitance, not quite as low as the ultimate cables, but sort of 10 times lower than a standard cable that you would get with the headphones. Now then, so just again, if we do this, so if we do 20 kilohertz, 25 picofarads, which is probably fair for one of these. Then you're looking at 318 kilo ohms, so 318,000 ohms, so 10 times the resistance across the thing. So again, as I said, very tiny effects. The other thing really with capacitors is, as I said, they're charging up and discharging, charging up, discharging. So if we put in a square wave, so the square wave signal's going in. So at the start of the wave, the top's going to be rounded off because that top bit is where the capacitor is charging up. And then when the signal drops back down, that again is going to have a curve to it because the capacitor is discharging. So it's going to affect the shape of the wave ever so slightly by having a capacitor. As I said, we've measured these, very, very low capacitance. These kind of effects are all going to be small, probably not noticeable, but is there. So one is it's going to bleed off some of those high frequencies. The other one is it's going to kind of mess with the shape of the wave a little bit, especially with very quiet, delicate sounds, because there's not a lot of charge going in to charge them up. So very, very quiet listening. It's probably going to affect it more than very loud listening. But again, the effects are probably not audible, very small. Just fun to mess around with and have a look at. But again, if you can make it smaller, like we can, why not? Oh, should we have a look at this one? Should we measure this one? Because this one is 2 meters, so it's a bit longer than the other ones that we've measured. So that's going to increase the capacitance a little bit. But let's just measure this one. 0. So this one is 60 picofarads, so not as low as the ultra low capacitance cable. I would have thought, you know, so this is 1.5 meters, this is 2 meters. I'd expect this to be maybe 30 if it was the same as these. The reason this is higher is because we've doubled up those wires, so you've essentially got 2 metal plates. You've got extra plates in there to build up capacitance, which is why it's slightly higher on this one. Obviously still much lower than sort of the 250 to 600 that you get on a standard cable, but it is higher on this one. It's quite interesting because the ultimate cables have got 2 twisted wires, the same as this one, but because these are so wide, it's spread them apart so well because of the way they're designed. It's dropped that capacitance below these, which only have a single wire. So yeah, it's just, again, it's those little design features. So this again, yeah, the two of those wires was too many. It's too many. Too many. Anyway, back to workshop Jason. So here I'm just prepping the end of the wires, adding a bit of solder to each of them, removing the silk carefully, and just join them all together so that when we come to add on the big old XLR connector, we can get a nice solder joint. Also, don't forget to add the boot of the XLR onto the cable before you solder the end on, otherwise you have to unsolder everything and put it back together. Done that a few times. Alright, next use a multimeter to test which wire is connected to which end, so we can figure out which is positive, negative, that kind of thing. Now here I'm just doing the last couple of solder joints, just making sure they're nice and secure on there. It looks a little bit crusty, but with lit wire and silver solder, that's about as sexy as you can get it, really, I think. Just doing the connector up nicely, and I've fattened up the wire with a bit of shrink tube, so when we add the grub screw in, it's going to hold onto it tightly, so if you yank on the cable, it's not going to pull it out. Obviously, with those big chunky solder joints, I don't think it's going to come away anyway. And there we go, we've got a nice chunky connector on the end of our cable. So there you go, that's how we made this cable. I hope that was vaguely interesting, or just relaxing, watching someone do a thing for a long time and jabber away. But if you would like this cable, if you have a pair of headphones that has 2 3.5mm Watsits and you want a balanced XLR, it's pretty high spec, it's going to be very, very low impedance, the capacitance is pretty low, connectors very expensive, feels pretty nice because it's cotton, it's a little bit heavy, but you know, these are the breaks. So if you'd like to win this prototype cable, and it's all tested, it'll all work nicely with the fancy aeco connectors, obviously make sure that you're subscribed, but stick a comment in the thing saying why you like it. So anything with 3.5, dual 3.5, 4-pin XLR balance cable, that's what you're getting. Stick your deets in the thing below and we'll check, and if you're subscribed, we'll stick your name in a hat, and then one of you will get this cable. I don't know, certainly the connectors is probably, I don't know, it's close to 100 quid worth of connectors, so it's probably a couple of £100 worth of cable. Yeah, it's worth having, and we'll be doing another giveaway probably beginning of next month. We've got a pair of headphones that we're giving away, so again, get subscribed, we'll be giving some more stuff away over the next month or so. But yes, I hope you found that interesting. Any questions, stick it in the thing. So yeah, I hope you enjoyed that, and I'll see you guys again.